Section 2.5 is the fundamental theorem of algebra. And this theorem basically says what it says here. A polynomial of degree n, that would be the highest exponent in there, just as a reminder, has exactly n zeros. Now, previously, we told you that it could have at most n zeros. Well, that's because we were talking about the real zeros. When we consider the complex plane, the polynomial will have exactly n zeros. So here we'll look at an example where we're going to factor a polynomial. Directions might say something like, write this as a product of its linear and or quadratic factors, and that basically means just to factor this thing down as much as we can. How we would do this, if we had no other tools, we would use the rational zero test from last section. We know that the rational zeros of this thing would have to have the form p over q, where the top number is factors of this constant, and the bottom number, q, I'm talking about a fraction here, p over q. The top number is going to be the factors of the minus 18. The bottom number is going to be the factors of the lead coefficient, 1. Well, that results in just the factors of 18. So we have plus or minus 1, plus or minus 2. I can do plus or minus 3. These are all factors of 18. Plus or minus 6, plus or minus 9. Yep, forgot the minus there. And plus or minus 18. And we could sit here and do synthetic division and try these things until we found one that works. Well, we're going to, some would call it cheating, but I really don't think it is. You have graphing calculators. So let's use them to our advantage like I showed you guys in class. What I'm going to do is enter this function into y equals, and I'm going to graph it. So I've already got this set up. I have already turned, here you'll see the function here. Okay, it's typed in how you would type it in. And the magic of computerized editing here, I've already got the window set up. And this is how it just took me a while to look and move the window so that it finally looked the way it was supposed to. And I came up with this nice graph. So I look at this and I see, okay, it definitely crosses there. The x-axis, if you notice, is going up by 1s. Okay, so when I look at this, that's 2. So I'm expecting that x minus 2 is going to be a factor of this thing because that looks like it goes right through 2. And that's the only 0 that I see. So when I look at this function, it says here degree 5, so that means it has 5 zeros. Well, this is a nice way to introduce the concept of repeating zeros. And that's going to happen when the graph just touches without crossing through. That's going to usually represent, or always represent, repeating zeros. And then the rest of them are going to be complex. We're only going to see, on the graph, we're only going to see the real zeros as the place where the graph crosses the x-axis. The rest of them are going to be complex. So it looks like -1 and +2. So what we're going to do is we're going to pick one of those and we'll start dividing here. So I will start with I don't know, let's start with the 2. So once again, the graph, we saw it was at, let's show that one more time for you. This would be the factor x minus 2, which means I put a 2 inside of the box when I divide. So we'll do synthetic division with a 2. So 2 goes inside the box. Now the coefficients, don't forget we need a coefficient for every term. There's no x to the 4th. I need to put a 0. I have 6x to the 3rd, negative 2x squared, negative 27x, and negative 18. And we'll do our synthetic division. You'll learn to appreciate this. It's a much quicker method than doing the long division. So hopefully you're getting pretty good at this process by now. Follow along. And as we were expecting, we get 0 remainder. That means that x minus 2 is a factor. So what's left over? The constant, the x squared, x cubed. This is x to the 4th plus 2x cubed plus 10x squared plus 18x plus 9. So right now, I'll put it in red just so we can keep track. Right now I know that x minus 2 is one of my factors for sure. Now what we can do is we can do the same thing here. So I am going to put this guy into y equals. Oops. Let's see here. There we go. To save time, I'm going to pause this video and I'm going to type all this stuff in instead of wasting time doing that, and then I'll resume here when I'm done. Okay, so we're back. I entered it in here, you can see, into y equals, and I graphed it, and we saw what we should have been expecting. We see a 0 at -1. Well, we already saw that one up here. Okay, so we could have gone directly to that, but if you forgot, you can enter that in. So now, that would be a -1 inside the box. So we'll go down here. Get our green on. Okay, so -1 goes inside the box. And now I have these coefficients: 1x to the 4th, 2x cubed, 10x squared, 18x, and 9. And we'll do it again, giving us a 0 remainder, as it should. Okay, there's the synthetic division. We got our remainder of 0, which we knew we would. And so what this is, constant x squared, x cubed. So I have 1x cubed plus 1x squared plus 9x plus 9. Now what do we do from here? If I can go back to my original graph, I think that was a good place to highlight it here. Let me turn the second one off and the first one back on. Oops. Okay, the window that I had set was -3 to 3, my 1, and then this thing down here, I had it at -50, 10, and I had the steps at 5, so it looked a little better. That was my graph. Remember I told you this is a repeating 0 because it does not penetrate the x-axis like this one does. So I use that to my advantage now. Now I'm going to expect another -1 root. So I'll divide by the -1 again. So I have 1x cubed, 1x squared, 9x, and the constant 9. And we'll do our division, bring down the 1, and off we go. And we get our 0 remainder. So I've got two factors here that I've demonstrated. Both of them are x plus 1. Because remember, it's x minus a -1, so it's x plus 1. Up here, it was x minus this number of 2. And then what I'm left with here, let's see what this is equal to. Constant x squared. So I have x squared plus 0x, so I'm not going to write that, plus 9, and that's what I got. Well, if I solve this for equaling 0 to get the rest of them, the complex ones, I know that this is not going to have a real solution. When I solve this, x squared equals -9, and so we are going to get the positive or negative, oops, x equals, forgot the equal sign there, x equals positive or negative square root of -9. Well, we now know what that is. We have a way to manage negative numbers. This is 3i. So I have plus or minus 3i. So what that means is that my roots associated with that, if that's the x value that it occurs at, then I have an x, oops, I didn't want that, I wanted it in red. Stick with my color coding here. I have an x minus 3i, and I have an x plus 3i, making a total of 1, 2, and I'll move up here. Whoops, let me do this without the pen. 1, 2, I've got the x plus 1 there, that's the third root, that's the fourth root, that's the fifth root. So I should have all 5 roots. What I encourage you to do then is to multiply these back out and see that you get back to the original function that we started with. So the completely factored version of this is going to be, let's go back up on top where you can see it. The original guy, this right here, will equal x minus 3i times x plus 3i. You know what, I'm never going to have room to write all this here. I better go down here, somewhere I got a little bit more room. X minus 3i times x plus 3i. Okay, those are the two complex or imaginary roots. Then I have two x plus 1s. And I had an x minus 2. This will equal that guy up there. If I multiply all that out, I'm getting right back to it, and this is a completely factorized version of that polynomial. One thing I do want to point out that I did not mention, but we introduced the concept of conjugates. X minus 3i and x plus 3i are conjugates of one another. We talked about that today and yesterday. They always occur in pairs. When you have a conjugate, you're going to see, when you have the x minus 3i, for instance, you will have the x plus 3i. So conjugate pairs, they occur in pairs. That'll be true whenever you have complex zeros. So if we look at a graph, we know it has 5 zeros. We can only see 2 of them, like the example that we showed here. Well, as you get more and more familiar with this, you're going to know that's 1, 2, 3, that's a repeated 0, anytime the graph just touches at one point like that. And then the other 2 are going to be conjugate pairs. The more you do this, the more you'll learn to recognize that. Now, this example that we did here is probably one of the more difficult ones that we're going to do. I think if you can get a problem like this right on your own, you are going to have absolutely no problem with the easier problems. Matter of fact, I can guarantee that some of the easier problems you can already do without any of this stuff. So if we focus on the difficult ones here, I think the rest of it's going to fall into place very nicely for you. So since I'm 13 plus minutes into this video, I am going to end this one, not to run over my 15-minute time limit, and I will put part 2 up where we'll look at some maybe a little bit easier problems, some that are a little bit less involved, and I would encourage the pausing and resuming of the video to try your own way. And we'll also look at one other type of problem. So this video will end and another one will resume.